everyone. Welcome to another Reimagine session powered by IT Labs. Thanks for everyone turning in online and everyone coming here. And for today's session, we have a very unique topic. It's about extracting entities and relations from financial data. And the person to dive in all this will be Dr. Igor Mishkovski. He's a professor at the Faculty for Electrical Engineering and Information Technologies, an academic researcher with a vast experience, and he has already more than 70 publications, both domestically and internationally. And his areas of focus include data science, machine learning, NLP, and a lot of other words that I cannot really pronounce right now, but I'm sure that he will give us all the guide on all that. Igor, please take the stage.
Thank you. First of all, hi to everyone. I'm really glad that I have the opportunity to participate in this session. So, as Marco said, I'm Igor Mishkovski, and I'm professor at the Faculty of Computer Science and Engineering in Skopje. And I will speak today about one research and business project. So it's a mixture between industry and research. It's not only research. It's about extracting entities and relation between them in specific financial data. As you can see, I'm not the only one here. I'm just the presenter and maybe the brain of this thing. So maybe like the project leader, but the main work was done by my student Ivan Krstev, who is abroad now. So I speak what he has done, and together with we work with Professor Miroslav Mirchev, another student Blagica Golubova, and another professor Sasha Gramatikov. So it's not only my work, but I participated quite a lot in this work. So actually, what we will see today, okay, I will give a short introduction to the problem and why the problem is important. Then we'll speak about, of course, we are speaking about data science and machine learning, so we need some kind of data set in order to solve the problem, which I will introduce later, just in several seconds. Some of the methodologies that we used in order to solve the problem and how we solved it. I will speak about the results. I will discuss the results, give some maybe drawbacks of the solution, or propose another possible things to do in order to improve the model, and at the end I will give the conclusion. So these are the keywords. So analyst ratings, name entity recognition, relation extraction. The people from data science, if they can see this, they know what I will speak about. Just this is more connected to finance world. So it's a mixture between finance world and machine learning. So NLP actually. Okay, so what is the problem here? We are dealing with financial data. That is more specific. We are dealing with analyst ratings. So I will explain what are the analyst ratings. So actually, we have people from big companies that analyze the stocks of companies of interest. So they give some professional, let's say, professional thought about what will happen with a given stock in, let's say, 3 months. So it's a long-term rating. And for example, analyst A is analyzing the stock for the company Apple. So he's giving, according to his knowledge and the data he has, so he's giving this prediction. So why is this important? Because for the investors or people who are in the financial world, they can use these analyst ratings in order to somehow predict the trend of the given stock, or Apple stock, for example, in the future. Actually, it will help in decision-making process of investors. So why are analyst ratings important? Here we have human experts who have all the data, who have all the knowledge in the financial world, and they give a certain rating. Of course, this is not the only approach. This is a more qualitative approach. We have also the quantitative approach, where we can use We can use historical stock price. We can use the news from for a given stock. Actually, first we have to find the stock for which we are speaking, like with the named entity recognition, the abbreviation there. So we can mix this up and have a quantitative analysis. But I here I had some references, but I delete them. So you have to believe me that according to other researchers, analyst ratings outperform the quantitative rating generated by machine learning, because it's not so easy to predict the stock. In several researches, you can find that analyst ratings is important. Yes, as I mentioned previously, they base their knowledge of, they provide their knowledge of trading activity statistics derived from historical data, and they use some external factors that can influence the company's operation and thus the price of the stock. Of course, we have an issue here. Sometimes this information is sometimes biased. What it means that it's biased because analysts, the people who are giving these ratings, the financial analysts, actually can make more optimistic projection for the stock price in order to, let's say, they have some relation with investment banks. So they have to give this, let's say, biased opinion. But what is the solution? If you have enough data from different people, from different analyst companies, we can easily, let's say, remove the noise of this biased opinion. So here is an example that we used. This is actually from the dataset. The problem is not so difficult at the first sight. So you will see, for example, Credit Suisse analyst Susan Roth-Katzke raised the price target on Bank of America, and then you have the ticker to $47 from 46, while maintaining an outperform rating. So this is the actual news that we are working on. Or you can see another example for some analysts from Morgan Stanley that raised the price target on Bank of America, and then you have the ticker to 42 from 38, while maintaining a underweight rating. So the problem here seems like it's not so difficult to find for the machine to find who is saying what for which company and what is the target price. When I'm speaking about target price, so you have the current price of the stock, and then you have the target price which the analyst is predicting. Of course, the problem becomes more difficult when you have, like you can find in the data in the news, you will find that M analyst analyzes N companies. So then the problem becomes, let's say, more difficult to solve. So at the end, so I will just, okay, sorry. At the end, what we want is that we have the people from that are analyst experts from a given analyst company. What is their prediction for the stock price? Like they have like in the next 3 months expect this price, and then we have the position, like the people should buy the stock. The people they're also suggesting if the people should buy, should hold, or sell the stock. And then you have also the action. These are the most important things from the data that we have, from the news, from the text. So you have also the action. So you have different actions. For example, if it's the first time the analyst is giving this opinion, is then initial coverage. They speak about, you know, initial rating, but they can change their opinion throughout time. You see, reiterated, like this means that he confirmed the previous prediction that the stock will rise. Is it okay with the problem? What is the problem here? So, so our purpose, or the purpose of this presentation, is to extract information which is of interest from analyst ratings. How to do it? We can do it only with the left side, which is the named entity recognition, like a task, NLP task, to find the important entities in the text. But then if we just stick up to the named entity recognition, we don't have the relation who is saying from which company to which company, and because, as I mentioned, the problem can be M analysts for N companies. So We also need another task in order to solve the problem, which is finding the correct relations between the entities in the text. So here is one example. What we did during this small project. Actually, we collected a data set, and then we, at the first thing, we tagged the data set, like Argus is the analyst company. This is the person from the given analyst company. He's giving prediction for AMD. You have the ticker for AMD. You have the starting price. You have the target price. You have the action, which is he's sure that he's maintaining his rating, and then the position is actually buy the stock because he says so. It doesn't mean that it's the truth, but at the end we will see how to find the exact knowledge. And here we have this. The first thing is the named entity recognition. This is just the process of tagging, which is the most difficult maybe thing to do because it needs a lot of data. Even though we do not have 1 million news, we have a small subset, but we will see that the model works also with this. And in the second part of this image, you will see also of this figure, you will see that you have a relation. You will see with the bigger is the relation. So it means that Jim Kelleher, which is the analyst name, actually works at Argus, okay? But he analyzes this company, and the company has this ticker. So we have also tagged the relation between the entities. So we have two tasks. First, tag the entities, and then tag the relation between the entities. So I will speak. Yes. In our case, it's changing a lot, but in our case, we didn't have a stream to. So we collected like statically. We collected. Now I'll speak a bunch of news. We make a snapshot and then use it. So it's changing frequently. I don't have the answer, but I. Don't have idea. Okay, it's more for finance, I think. But what we actually pinpoint like important things. So we have the name of the person who analyzes the stock. We have the company who is employing the analyst, a company that is being analyzed. We have the ticker for a given company. We have the position, whether should be bought, held or sold. We have the action, which is this is like changing the opinion of the analyst. We have the price target and the price start of the stocks. The position, a more specific review of the position, you will see that in the text you will not find like buy, sell, hold. It's not so easy. I mean, it's not the keyword search like buy, but they have a different. This is more also for finance people, but you have different ratings they give, like analyst buy rating, which means you should buy the stock. A strong buy, which is for sure buy the stock. Then is the outperform rating, which means that the stock is outperforming the average stock price on a given SP 500, I think. I'm not sure. But however, it's outperforming the average. You have analyst market perform rating, which is it's going as the market is going. So it's not too much down, too much up. So these are actually the positions that they are giving. Then you have the analyst hold rating, which is hold the stock. It's quite easy. But then you have analyst neutral rating, which is I don't know what to do. Okay, it's not hold, it's not say, it's not, I don't know. So they're giving also this kind of rating. And then you have the sell rating, which is sell, strong sell, and then underperform, which is the stock is not so will not perform so well. And for the action, also here it's not the keywords. They use actually we define these keywords, but they use different words in the English dataset. So like upgrade, downgrade, reiterate, initiation. So this is my first rating. There is no change. Like I stick to the previous initial position. Then downgrade, which is he changed the opinion from something from the blue to the from up to down. Okay, this is the downgrade. We have the upgrade. He changed the position from down to up, and that's it. So Yes. Okay. Okay. As I mentioned, again, this is the same slide. So we have the named entity recognition tagging, and we have you will see that this is one actual news. You will see that you have a lot of things in one sentence. So a lot of people from a different companies and are analyzing a lot of stocks for different companies. So it can happen this kind of, let's say, a mess. Then after defining the entities, we define this relation. So we have the simplest relation, analyst name. This is the one entity which I mentioned before, and analyst company is another entity. We just make a relation like analyst works at. Then analyst name analyzes company A, and then because sometimes in the news there is no name of the analyst, there is just the analyst company, so it can be also inferred that the company is given analyst company is analyzing a certain company. Then the company has a ticker. This is quite straightforward. And then we have the position, the action, like position, strong buy, hold, sell. The action which is reiterated, initiated, downgraded, and upgraded. Price target, the projected price, and the current price are also connected to the company which is being analyzed. And we have now on the other side, we have who assigns position, action, price target, and price target for the company that is affected above. Okay, so it's not the big data set, so it's 1,000 because we didn't have so main force, so it's like 1,000 analyst ratings. We used the English language. Some information, the longest had 1,100 words inside, the shortest only 9, so it's quite diverse. But if you check it, then in average, the ratings have like 79 words, and 50% of them are longer than 51. Just some statistic. In general, they were like concise, what we collected, because we randomly connected and had a similar structure. But okay, we used 20% for testing, and also we tried, because we knew German language, we also collected the German from the German dataset and make the annotation properly, the same way like we did for English, because we used only 100 of them used for testing, and 100 we infiltrated in the English corpus. So the idea here is not to use a multilingual models. So we use multilingual models that can use knowledge from different languages. So they are trained on multilingual dataset, on multilingual news. So here we actually 100 of them, because they are not so much, we put them in the English dataset, and we try to predict in the test phase, we try to predict 100 German. We will see the results later. Just some statistic, what we have as a distribution. This is the number of each label that we have, actually entities, and the relation, the number of relations which we have in the dataset. Nothing special about that. So this was the introduction and the dataset that we used or generated for this problem. Now about methodology. So what we use here is, okay, we have the training data for name entity recognition, and we have the relation extraction training data. So we have 4 different, we have the embedding model, which is actually trying to generate a numeric representation for the given text, because we have to have some numeric representation. We have this embedding model we use in both components, and the both components are actually the NER component and the array component, and we have some classification layer down that is using the vectors from the embedding layer. And using this and the training data set, we generated the 2 models, which is the NER and array model, and use both of them when the new data comes in, and to have the inference on the new data. Now here we have, it's not the only solution here, because as you notice, we divide and conquer. So we divided the problem in 2 subtasks and train both of them, and then use the new data to infer the result. The result. So when we infer, we actually expect the same table as I showed you like some structured data to have at the end. However, this is not the only solution. Actually, we have one of the comments, and it was rejected because of this. But it's not that it must be done. That you can have one model for both tasks and to have multitask learning. So instead of separating the two components, to have one component and to create one model for this. We thought that what was our idea behind this was, this is not a so difficult problem today, okay? To find the entities in the text, it's quite easy. So instead of having one, because this is not so easy to find the relation between entities. So instead of having one big model, here we can use a quite simple model, and here we can use a bigger model. So in this way, we can affect the performance of the in production, let's say, when we use this service in production. But of course, in the research community, they wanted they wanted one model because it can improve accuracy by 0. some percent, or which is by our opinion not so important. So our approach is actually based on pre-trained language models. The good thing is that we have already trained. We don't have to train a language model. We used different types of pre-trained learning language models, like the Google's BERT, then Roberta. Then we use the bidirectional LSTM trained on huge corpus in order to check if a simpler model will work. It doesn't have to be a transformer architecture. Okay, for the NER, the output of the pre-trained model is used as an input. So we have a pre-trained models from above, language models, and their output is used as an input to a simpler classification model for determining the final label. So here is a classification problem, okay? We have to determine the label. But here, instead of classifying entities in the relation extraction, we have to classify the possible relation between entities. So in both tasks, in both NER and RE, we are using a embedding model that transfers the text into vectors, and this is the central dogma for NLP in general. As I mentioned before, we had different approaches in order to tackle this problem. So the first approach that we can use both components, the named entity recognition and the relation extraction components, can be treated as a single language model. And the second approach, I will skip the two options of the first approach, is to train two components separately and only connect them during inference stage. As I mentioned, we stick to this approach. So yes, the time complexity increases, but we gain on simplicity in the overall architecture. So we can divide the problem in two subtasks, and one of the person can be responsible for NER, one of the persons for RE, and we can also integrate a simpler model for NER, name entity recognition, as I mentioned before. Okay, and in the first approach, we can use the embedding layer, one embedding layer that is shared between the two components and updated in a mutual fashion. What does this mean? It means that we have a multitask learning. So, of course, when we have multitask learning, we are learning two things with, let's say, one shot. So we have a faster training, and we have shared embeddings for both NER and RE. So actually, the embeddings from the language model, we fine-tune them for our problem, and here we will have shared embeddings for both tasks. This is the first option of the first approach. And the second option is to train the two components together. So as a one component, but with separate embedding layers. Okay, so we will have a different, how to say, we will have different embeddings for the trained embeddings for NER and different trained embeddings for named relation extraction. Of course, the training is slower, but cancels the problem with performance compatibility of language model for NER and RE, because we have two embedding models. If let's say sometimes one language model is better for NER and the other language model is better for RE. It can happen. In the first option, we are actually using only one embedding model. So this can make some issues. However, our approach was this. So it was simpler one, and we had some, why we did it, I explained it before. For the NER, there are also additional, for this task, there are two additional alternatives. So we can, the first thing is we can fine tune the transformer layer on the NER task and only use a simple linear model for the token classification. This is the first thing, or we can directly use embeddings from the pre-trained language model and deploy a more complex classification layer. So it's like we are changing this means in order to make the house stable, we are changing how it's called, the basics of the house, okay? But here we don't do this in the second approach. So we are making something above more complex. So we use this kind of approach for the NER task. So we fine tune the transformer layer on the NER task and use a simple linear layer above in order to classify the entities. Okay. So for the embedding model, now I'm going into details. What we use masked language models because it is known that they perform best for sequence labeling, which is a NER task. So we label some sequence, which is a NER task. So what is a masked language model? They have a big corpus of data and they mask certain words. That is, they remove the word, or they put a random word, or they put the actual word, and they learn the context. They represent the word in a vector, but the vector actually explains the context of the word in a given text. So this approach is quite, I don't know, like 7 years old, maybe. So it's like we use the Google BERT, Roberta, distill BERT, which is when you see a distill, it means it is a distilled version of the BERT. So it means a little bit pruned, chopped BERT. And we use Talbert, which I will not speak so much because it didn't give some result. And we also compare it to one of the not so deep, not transformer architecture, a deep network, but the bidirectional LSTM. When you have you are training the LSTM in two directions in order to predict the entities. We had in the last embedding model, we used already trained Facebook Flare embeddings, which they have data. They train they have the embeddings for the word, and we use also just to see a non-contextual globe embeddings. Here, when you use the globe embeddings, you lose the context. Okay, if the word is, I don't know, one word has two meaning in a sentence, in one sentence, another meaning in a different sentence, they will have the same vector, okay? Which is not correct because the word in one sentence means one thing and the same word in another context means another thing. So you lose the context with the globe embedding just to see, we wanted to see how it performs. Okay, BERT is a bidirectional transformer that is, we use the masked language model because it's needed for this task. Some specification, it has 12 transformer blocks, 6 encoders, 6 decoders, with 768 dimensional hidden size, and it has 12 multi-head self-attentions. If you collect all the things that it has 110 million parameters, which is not so big. In the machine world, I think it's not so big. Billions is a little bit problematic, like GPT-3 and so on. So it's not so scary. And I also use the distilled version of the BERT, which is like half of the parameters that the BERT has. Also, Roberta, what is the difference? We use also Roberta for both tasks. What is the idea? What is the difference with BERT? So BERT is trained on a little less data. So on less data than Roberta. This is the one good thing about Roberta. Also use dynamic masking. What it means, dynamic masking, throughout the epochs, BERT is using the same mask words, okay? So he chooses what to mask, what to hide, and throughout the epochs, he doesn't change this. In order to be more robust, like Roberta is robust compared to BERT, he's actually changing the mask throughout the epochs. In this way, he learns he's more robust, and he uses a larger batch size, which is just good for training performance, because when we have larger batch size, we're improving the performance, and uses tokenizer, which is a byte pair instead of word piece tokenizer. Bertrand uses word piece. I will not go into details. It's a probabilistic character aggregating the characters in the sentence by their frequency, more or less, or like maximum likelihood. What we use also, we use two different libraries. We use Spacey, a quite famous library. We use Flare, which is not so famous, but it's okay. It's from Facebook research. So in the Spacey, we implemented, as I mentioned, 4 different transformers. In the Flare, we didn't use transformer architecture, so we used the simpler architecture, which is a bidirectional LSTM. So, but the good thing is that you can stack the embedding. So it means that, let's say, you have a one word, I don't know, pray, and pray or teach. You have the teach, and you have you can embed the embeddings, the vector representation with, let's say, from non-contextual from contextual embeddings. So you can enlarge the embeddings for. This is a good side from this library Flare. Okay. Now we are going with the NER component, going into more details. So what we had to do, okay, the data, the data was text. We tagged the text in a given platform, UBI, so I think the platform is called. We tagged the data, then we had to extract the data in this format. This is quite used format for NER task, for name entity recognition. So it's a beginning, intermediate, or out. So you will notice that Switzerland is the beginning of a location, and then stance is not an important entity. Okay, this example doesn't have anything with finance, but you will notice that Alphonse, it's a person, but he has a surname D'Amato. That's why you have an intermediate before the per, which means a person. Okay, and also in order to learn more, we use not only the labels, but we use using Spacey library. We use the part of speech tags. So it means a noun phrase, a verb, and so on. So this can additionally enrich the data, and the model can be more accurate when he knows if it's a verb, if it's an adjective, or noun. Okay. This was the first thing. Then. Okay, the pipeline used to perform a NER test consists of an embedding model transformer. So one of these transformers, we use different just to evaluate the results, and consists of a single linear layer to the transformer. So we have a linear layer above the transformer in order to make the classification. We used case-sensitive variants of the 5 different transformer architectures, BERT base case, distal BERT, Roberta, I already speak about them, and here we use the multilingual part. So this is a model that can transfer learning from English to German, from German to, it can be used in translation tasks. We just want to see how the model will function when we has a text in German. So if it will work also on this. For the Flare, so here, I was explaining this part. For the Flare library, we use the same pipeline architecture. The only difference is that we add additional recurrent neural network layer between the embedding model and the linear decoder. So it means that we a little bit add additional complexity to the problem in order to improve the results. We utilize, as I mentioned, stacked embeddings, so overlaid embeddings above. And here we played with non-contextual, with contextual Flare forward and backward, or BERT embeddings, which are also contextual embeddings. For the recomponent, the problem is a little bit, it is a little bit more difficult because we have to find the relation between the words in the sentence. So what we used here, actually, we created a matrix E. This is a matrix not for the whole data set. This is the matrix for one sample, for one document, okay? And if you see, it has 3 indexes. So you have, for example, I will speak about A1 to 1. So usually an entity can be 1 token, but it can be also 2 tokens, 3 tokens, United States of America. So it's a location, or Apple Inc. So it's 2 tokens. So this is actually, if you go, this 2 means the second token from the entity. This means the first index 1 means that is the first entity in the document. So actually the document has M entities, okay? It has M entities, and these are the first, the second word, and so on, of the first entity, the first token, the second token of the first entity. And if you go with the number of columns, the number of columns is actually the size of the vector, which is the embedding model, actually 768. Depend on the model, but here for BERT, we use 768. Here is the example. So we use different, here I have mistake. We use max pooling operator. It's not averaging. What it means that now we want to extract, the 2 tokens to find the maximum pooling function and to have 1 representation for the entity. So even though the entity has 3 tokens, we just want 1 vector representation. It doesn't have to be this way. We tried with average, with max. Max was better, so this is my mistake. What else here? Yes, we obtained a single vector per entity. So this is the first vector for the, this is the vector for the first entity, the vector for the second entity, and so on and so forth. However, then we had to map this into relation. So, for example, the first entity was the analyst. This is the vector representing the analyst name, Igor Mishkovski. Okay, he works at Finky. So this is the entity, the vector representation for the second entity that has a relationship works at. Okay, so this is actually in the example is works at. Then it's like the other relation is has affects and so on and so forth. So we put in this matrix form for this is matrix form for 1 document. So we created this matrix form with the possible relation in a document. Here we had a discussion, even should we also put the entities that do not have relation, okay? Can we learn something from them? We decided to use only the entities that have some relation, not to add the entities here that do not have, like this pair of entities. If they don't have relation, they are not in the matrix, only the entities that have some of the mentioned relations. Okay, when we use the library, they had a similar approach. I mentioned the difference. The only difference was this RNN layer that we had. Of course, they use different library space uses Sting, Flare uses PyTorch, but nevertheless, we had the same training phase. Another thing that we noticed is that 95% of the 8 entities that share a relation are with a window of 40 token radius. So this is a little bit of statistics. So we thought that this could help the decision process. So if you when the person mentions, let's say, a rating for a given company, the price, the target price is somewhere near. It's not in the at the end of the sentence. Even though in 5% it happens that he speaks a lot, and then he gives the price. But 95% was not the case. So we also try to discard all of the relations that are not with the predefined window in order to improve the accuracy of the model, because sometimes it can confuse the model if they are long. And also another problem with the previous transformer architecture is that they cannot see so far, like they cannot see more than 500 tokens in front, okay? So of course we have different architecture. to catch this, but we didn't use in the paper on this research. Okay, as I mentioned, we didn't stick only to English. We trained a multilingual model using data from multiple languages. It's not so languages. We used the English and German corpus, and we tried different multilingual versions of similar Distelbert multilingual, Flare embeddings multilingual. All of them Spacey provide. I mean, Spacey not provide, but uses these transformers for multilingual, and also Flare, Facebook Flare uses multilingual Flare simpler encoder. So what we get, so I mentioned we divided the data set. So what we get for the NER task first is that as I mentioned, NER is not so difficult to solve, and we do not have so many entities in the text. We have, you can count them in 2 hands. So we had an F score, which is quite good for this task, like 97% F score of precision recall are good. So, and the best case was with Roberta base. With Roberta, okay, forget about the base. Of course, this is like you cannot see too much difference in the result. You can see that Albert has that's why I mentioned that I will not speak about this model because it ruins the result. But we also analyzed the performance of the model. So usually in machine learning, this is important slide. Sorry, this is important slide. Okay, so okay, I have 98% accuracy, but this model is quite heavy. Okay, this model means a lot of GPU power and quite slow inference. So nobody likes a real-time processing with this kind of model. To wait several seconds, 500 milliseconds when it can be quite faster. So we noticed the GPU memory allocated. So Distelbert, this is the lightweight version of the BERT. This is the time minutes. Yes, this is the GPU memory allocated. So you can see that I don't recall the size of the GPU RAM, but nevertheless, it has 50%. It occupied 50%, I think, not more than 12 gigas. So it means 6 giga is the model at the most. And here we have the speed. So you will notice that this goes up. And if you want in production to be fast, then also Distelbert is a good solution. You can see that Distelbert is quite close to the best one, which is Roberta. So actually, we decided that Distelbert is the solution here for NER. Even though you will also notice another thing, if you use non-contextual GLOF embeddings this is the different library which we use, the Facebook Flare, and we use non-contextual embeddings. We don't have the graph because it doesn't support this library for showing the GPU RAM. We could have extracted, but we didn't, and the speed. But you will notice that only using non-contextual, you see the NER task is quite good. I mean, close to the Roberta, which is heavy. And this is, you can execute on CPU. Okay, so you don't need the GPU to do this. You can also do it on a CPU. Here is a combination like Facebook has trained a contextual embedding in a forward and backward direction. And we stacked the non-contextual above, and this was maybe the best result we get with the Flare library. Also, we used instead of GLOB, we used the BERT. We had similar results. So the conclusion from this is that for the NER task, we don't need the heavyweight model. Now, the results for the relation extraction. So here is the results, the precision recall and F1 score here is integrated. We have the Spacey transformer model integrated in Spacey, and we have non-contextual. What you can see, as I mentioned in the beginning, the relation extraction, you see the score is quite awful for non-contextual embeddings. I mean, it's not random because it has a lot of relations, but it's not satisfying. We get the best result again with the Roberta, and yeah, if you measure by the F1 score, the best is with Roberta, so we extract the relation the best. But Distelbert is still going well, like hand in hand with Roberta. Another analysis we did is that throughout the statistic, we find that 90% of the entities that are important to find are not more than 40 tokens apart. So what we did, just to check if we can improve the model, we just remove, we didn't search for, if you find a company, then look it in the 40 tokens. If you find analyst company, then look in the 40 tokens plus minus, 20 plus, 20 minus. So this is without a proximity cleaning. So I will call it proximity cleaning. And you can see that the results, of course, are improving for when you have this kind of knowledge integrated into relation extraction. Yes, and I mentioned that we also use pre-trained multilingual models. We use the BERT, multilingual Roberta, distal BERT multilingual, and we use also the FLAIR multilingual forward and backward contextual embedding. So we used all of them, and again, of course, Roberta was good, but here we had 1,074 English samples. We use them in the training set, and we have 100 German concatenated in the training set, and we use as a test set only the 100 remaining German. So it's not so, we didn't have so much data in German, let's say. We didn't have time to do it. Further, we are also good. BERT, here BERT shows better result, but not so far. And it was surprising for us that FLAIR multilingual, if you can notice in the English in the previous slide. So here it was FLAIR forward and backward was not so comparable to Roberta, but when you go to multilingual, it shows quite good results. I mean, comparable to Roberta. Okay, and okay, we did these experiments. We have the models for NE, we have the model for E. What is also good is that in the pipeline, we first, let's say the data, the new data comes in, then we detect the entities, and then we have some, sanity check if everything is okay. And then we use the relation extraction to find the relation between the entities. Because if the first component doesn't give the proper results, then we do not use the relation extraction component. So this is also one plus that why we use these two different architectures. At the end, we played a little bit with the graph database. So why we did this, I will explain later. So it's actually data-driven representation. It doesn't have to infer connections, through foreign keys and so on and so forth. I think you're familiar. So a graph database is purpose-built to handle highly connected data. It has flexibility, it has agility, performance, and so on and so forth. So we try to build the knowledge graphs using the two components. We have the NE and RE, and then we use this to build a knowledge graph. So the NER entities are actually the graph nodes, and the relation are the edges that makes the relationship between the nodes. This is in the beginning, in the starting phase. So the idea here is, as I mentioned in the beginning, you have the bias. Some person from Morgan Stanley has always pushed this stock up. Okay, but if you have this graph, you can easily find this. You can easily find the clusters. You can easily do network science or network analysis on this and try to extract the knowledge from the graph. This is the next approach. We are working on this. At the end, almost at the end. Sorry. So, don't know if you can see view, no. So at the end, we built, a service that endpoint that actually receives the new text. Okay, publication date is not important, and it gives the relation in this kind of form. So you have the company Alibaba. This is the company. This is the root because this one is being analyzed. And then you have the positions in order to mark the company in different color or to select the company. Then you have the ticker, which is Nusebaba. Then you have the entity position of the ticker. Then you have the ratings. So as I mentioned, one company can have several ratings. So that's why you have the ratings, and here can be a list of ratings that some Mumbai from Goldman Sachs, here is the action downgraded, the price target, and the price target. This is actually the service working and giving the result, which are quite good. So all the relations and all the entities and all the relations were extracted correctly in this example. Of course, I was searching for a good example. And here also, as I mentioned, the service is robust, so it can also, if there are more companies being analyzed, it will be a list of companies that are being analyzed. So we have list of lists in the endpoint. So the output is like this. And this is used in the Neo4j in order to make the knowledge graph. And then the analysis is missing at the end to extract the knowledge from this. This was the inference. Yeah, this was the inference part. I shared the, I shared the Swagger output. The JSON output, sorry. What is the conclusion? I think I'm on time. What is the conclusion about the work we did? So we explore the utilization of analyst ratings in stock analysis. We collect, this is an important task because we collect and annotate a data set of this kind, which there are not so many data sets like this. When we search for data sets, there are no there are providers for news, but you have to pay, but they are not annotated. So we try different libraries, Spacey and Flare, for both NER and RE. We also use different architectures like transformers, bidirectional LSTMs. We also annotate small additional corpus in German, so to provide a multilingual. And the good thing is that when we do it in German and in English, we can also do it, learn in Macedonian. So it's the multilingual, not so good, a little bit less performance, but it can infer also in Macedonian. So this was like a mixture between academic research and the need of a certain company. So it's like, you know, when we symbiosa, when we stick together, I think the results are good. What is the future work? So yes, of course, the data set is quite small. I mean, it's not to be proud of 1074, but still. Then I mentioned that we have the issue with the long, you know, in the news, like the analysts, and you have, I don't know, 20 sentences, and then you have the price target. And this is not catching, our architecture is not catching this kind of long relation, but there are architectures that can easily, not so easy, but they can leverage this, we can leverage this long transformers architecture and try to find. Of course, the models are plain, so we didn't do any pruning of the models or reducing the parameters, because on production it will be, if you use the best model, it will be slow. But of course, we can do optimization on these models. For like Microsoft has this ONNX runtime, so you can infer from a reduced model. So you can prune, you can do quantization if you want, you can do pruning of the graph, you can change the structure of the graph. So this is provided with this library. And of course, the part that is missing, the Neo4j analysis or the graph analyzing from the data. So I don't know, I didn't measure the time. I hope I'm on time. Thank you for your attention, and that would be it.
Do we have any questions? Anyone? Let's just make a quick check.
Oh, yes. Okay. Okay. Mm-hmm.
And then we have the first embedding, for example, which is your example, and the second embedding works at. So.
No, we have the second entity.
Yeah. Okay. The second. Okay. The
that is related. Yes.
And how do you label the relation?
Work set. Like a class. Your classification. Yes, yes. It's but you need to transform just to this matrix, and then it's a multi.
And then firstly, it's labeled manually.
No, we infer,
Or
no, we infer from the tagging platform.
from the thing.
Yeah. Then we annotate there, and then from there when we convert this into matrix, we infer from the annotated data.
Okay. And the labels for the different relationships?
In the annotated data there, because we annotate also the relation. Well, like in the platform, you select the entity, you select the second entity, you draw the line. This is this is the most difficult thing. You draw the line, and then on the line you put the label work set, and you do for all the relations in all the 1047 documents. And then from this you have it in the in the JSON format or IOB or whatever. And then we can generate the matrix using the embedding model for the two entities and output class using the annotated data. Yes, yes, but only two words are used as an input. Yes. Yeah.
Okay, thank you. Let's just make a quick check online.
Okay.
Questions there. Okay, anyone else here?
Yes.
Professor, you have mentioned that you are using a sanity check between,
Mhm.
because you have separated the process, you have used a sanity check. Can you give more details on how you do that sanity check?
Yes. So here this is like hidden thing. I mean, I didn't show it, but first, usually analyst makes not only ratings for a companies, but for a given, let's say, a market. It can also say that I don't know, also financial instrument like I don't know, the oil price. So this is one thing also. So in the beginning we catch if we have all the entities there. Okay, this was the simple sanity check, but then we realized that sometimes they give the ratings for a financial instrument like oil, gas, something like this. No, now we actually we annotated the data. This is in the meanwhile. We annotated the data also with this kind of information, and we have another service that is actually checking what kind of entities. If it's a company, if it's a company, if it's a financial instrument, if it's some kind of market. But this is a different model that. So now we have the thing instead of the company. I show the company, but now we have the thing. So if we have the tags, let's say the thing, which is the company, either the analyst name or the analyst company who is analyzing, and we have the action, the position, not the action, because sometimes it's missing. Then we can go to the re. More or less is like this, the sanity check. Just three if conditions, though, nothing special. Okay. Thank you.